This is one possible future for a stock, one path, one story, up 7% over the year if you trust this picture. But here's the thing about serious traders. They don't predict returns. They trade distributions, because every single price you see is just one sample from a much bigger object. A cloud of futures, each one equally consistent with the same starting point, the same drift, the same volatility. Back in episode 1, we derived this equation. ds equals mu SDT plus sigma SDW, the math behind every stock price. And this equation doesn't give you a number. It gives you a whole distribution of futures. So when someone asks, where will the stock be in a year, a common answer comes out. $108. The expected value, one clean number, but that one number is a ghost. You'll never actually see it. It's the average of a thing that has shape. The real answer, the honest answer, is this entire shape. 90% of the futures land somewhere between $76 and $147. The expectation sits in the middle, but the spread is the story. That spread, right there, is what you're actually trading. And the grammar of distributions has a name, probability, omega, the space of every possible future the market can take, f sub t, the information you actually have at time t, and the expectation of x given f sub t, the best guess you can make using only what you know. 3 ideas, 3 symbols, and every formula in the next 8 episodes of this series, Black-Scholes, risk-neutral pricing, Ito's lemma, is built out of these 3 things. Probability foundations, the language of finance. When new information arrives, beliefs must update. The math of updating has a name, and it is 260 years old. Start with any space of outcomes, omega. An event A is a region inside it. A second event B is another region, which may overlap A. If we learn that B has happened, the world contracts. We now live inside B. The probability of A given B is the fraction of B that lies inside A. That ratio is conditional probability. Rearranging the definition gives the multiplication rule. The probability of A and B equals the probability of A given B times the probability of B, but the same intersection can be read the other way. P of B given A times P of A. Set these equal, divide by P of B, and you arrive at Bayes' theorem. 4 pieces, each with a name. Posterior equals likelihood times prior, divided by evidence. Thomas Bayes proved this in an essay published after his death in 1763. Pierre-Simon Laplace rediscovered and generalized it a decade later. Every modern inference engine, spam filters, risk models, medical diagnostics, market makers, is a descendant of this one equation. Here's what Bayes looks like in a trading room. Before an earnings report, the market's belief about tomorrow's return is a distribution, the prior, centered near 0, standard deviation around 2%. Then the earnings print. Revenue beats by 3%. That is new evidence. Bayes' theorem tells us exactly how to rewire the distribution. The prior times the likelihood of that particular surprise, normalized by the total probability of any such surprise, gives the posterior. The distribution shifts. Its mean moves up. Its spread narrows. This is not metaphor. It is the mechanism by which option prices reprice in milliseconds after an earnings release. Markets are Bayesian machines, running on the same equation a Presbyterian minister wrote in the 1760s. One last piece. To compute the denominator, the total probability of the evidence, we sum over all the ways the evidence could have occurred, weighted by how likely each underlying state is. This is the law of total probability. With it, Bayes' theorem is complete and beliefs can be updated. Next, we give beliefs a summary. Expected value is the most misunderstood number in probability. It isn't the average you'd see, it's the average you'd see if you ran reality 1,000,000 times. Start with a fair 6-sided die. 6 outcomes, each with probability 1/6. Multiply every value by its probability and add them up. The expected value is 3.5, a number you will never actually roll. Now bias the die. 3s through 6s are twice as likely as 1s and 2s. The expected value shifts to 3.9. For any discrete random variable, the recipe is the same, sum x times p of x. For a continuous variable, the sum becomes an integral of x times the density. Expectation has one structural property that dominates every calculation in finance. It is linear. The expected value of a linear combination of random variables equals the same linear combination of their expected values, a times x plus b times y. E of that equals a times e of x plus b times e of y. And critically, this holds whether or not x and y are independent. The proof needs only additivity of measure, no extra structure. This is the sentence that makes portfolio math tractable and option pricing possible. You have seen this equation before, in the third episode. 3 assets, 3 expected returns. Take the classic 60-40 portfolio. 60% in a stock earning 12%, 40% in a bond earning 5%. Linearity of expectation says we don't need to track any correlation, any joint distribution, any second moment, just the weighted sum. 60% times 12 plus 40% times 5 equals 9.2%. The portfolio lands here on the expected return axis. This simplicity is the reason portfolio theory works at the level of means. It also sets up a warning, because as you will see next section, variance does not behave this way. One more connection. The expected value is what you converge to by averaging outcomes from many trials. Sample mean of n draws, as n goes to infinity, approaches the true mean. In the fourth episode, we used exactly this to price options. Average 1,000,000 simulated payoffs, and you have a Monte Carlo estimate. Now we have what the center looks like. Next, the spread. Risk isn't the loss you suffer. Risk is the spread of the distribution before you know. That spread has a name and a number. The name is variance. Formally, variance is the expected square distance from the mean. Algebraically, expand the square. 2 of the terms collapse against the definition of the mean. What you are left with is the one identity every quant uses. Variance equals the expectation of x squared minus the mean squared. One definition, 2 forms. Use whichever is easier to compute. Watch what variance actually mean, not as a formula, but as a shape. A standard Gaussian, mean 0, sigma 1. 50 samples dotted along the curve, the reference world of probability. Squeeze sigma down to 0.5. The curve pulls inward. Samples crowd the center. Outcomes become tightly predictable. Now push sigma to 3. The curve flattens dramatically. Mass spreads outward. What used to be a 3 sigma tail event, a rare shock, now happens routinely. Back to 1. The mean has been 0 the whole time. Same expected value, completely different worlds of risk. The classical reference is 1 sigma holds 68.3% of outcomes, 2 sigma, 95.5, 3 sigma, 99.7. The shape never changes. Only the width tells you how much can happen. That handles one variable. But the world rarely gives us one variable. We have stocks and bonds, returns and volatility, pairs, triples, whole portfolios. Covariance measures how 2 variables move together. Positive covariance, stocks rising on the same good news or falling together on a crash. Negative, bonds climbing while equities fall, the classic hedge. 0, movements that are uncorrelated. Each variable acts as if the other does not exist. With n assets, that single number becomes an n by n matrix. Capital sigma, the covariance matrix. Diagonal entries are variances. Off-diagonal entries are the covariances. Every phase 2 formula you will see, Black-Scholes, risk-neutral pricing, portfolio optimization, is written in the language of this matrix. One last distinction, easy to miss. Variance is measured in squared units. Squared percent, squared dollars. A strange quantity. The square root, standard deviation, restores the original unit. It is what traders actually quote on every desk and every currency. Spread done. Next, time and information, and how both transform a distribution. Time in finance isn't just a number on a clock. It's a flow of information. At any moment, you know what happened up to now, and nothing about what comes next. So what exactly is the information you have at time t? Every serious pricing formula depends on answering this precisely. Remember the binomial tree from episode 2. Each step, the stock goes up or down by some factor. At any time, the history you know is simply this: which way did each coin flip? At time 0, before any flip has happened, you know exactly one thing. The starting price, 100. That is F0, the smallest possible information, the trivial starting point. One coin flip later, there are 2 possible histories, up or down. You can now distinguish 2 scenarios. That's F1. After 2 flips, 4 possible histories. F2 contains everything F1 knew, plus every new distinction the second flip revealed. 3 flips, 8 distinguishable histories. The branching doubles each step. 4 flips, 16 possible paths through the tree. F4. Here's the critical property. Each later sigma algebra contains all the earlier ones. Information is never forgotten, only accumulated. What you knew at time 1, you still know at time 4. This is not automatic. It is the defining feature. A growing family of sigma algebras, one for each time, with this nested inclusion, that is a filtration. It is how mathematicians make the phrase information over time precise. The formal statement, a filtration, is a family of sigma algebras, ft for each time t, with the nesting property. If s is less than or equal to t, then fs is contained in ft. The starting point f0 is typically trivial. You know nothing beyond the overall sample space, and the family keeps growing from there. This concept was formalized by Andrei Kolmogorov in 1933, in the same paper that axiomatized probability theory itself. Once we have a filtration, a stochastic process is called adapted, if at every time t, its value is already determined by ft. The stock price is the canonical example. You only know today's price today, never in advance. A stronger concept is predictable, a process whose value at time t is already known one step earlier, at time t-1. Why does any of this matter? Because every pricing formula, every hedging strategy, every martingale we will ever meet is an adapted process. The trader can only act on information they actually have. Next, we use filtrations to define conditional expectation, the single most important tool in quantitative finance. Here is a simple-sounding question with a profound answer. What is the best guess for y given x? Not just a number, a function. One best guess for every possible value of x. Be careful with the notation. E of y given x is a random variable, a function of x itself. E of y given x equals little y is the number that function produces at that particular y. Function versus number. Let's see it emerge visually. We drop 500 data points, x and y pairs, sampled from some joint distribution we don't need to name. It looks like a cloud, messy, noisy, no obvious relationship at first glance. Now slice the x-axis into 20 thin vertical strips. For each strip, take only the points that landed there and compute the average of their y values. One golden dot per slice, the bin mean. 20 answers to 20 conditional questions. Each dot is the best guess for y, given that x fell in that slice. And watch what those 20 dots trace out. A curve, a prediction, a pattern that was hiding in the noise. For this data, that curve is 2 plus 1/2 x. The conditional expectation made visible. This isn't just a cute picture. Conditional expectation has a precise characterization. E of y given x is the function f that minimizes the expected squared error. It is the L squared projection of y onto the space of functions of x, the best least squares predictor over every possible measurable function, and a second property, the Tower property. The expectation of a conditional expectation collapses back to the original expectation. Information can only refine predictions, never shift them on average. On our Ep02 tree, 3 conditional values, each known at time 2, weighted by their probabilities, collapse exactly to 101.83, the unconditional expected price. One crucial caveat. For the data we drew, the conditional expectation happened to be a straight line. That's why simple linear regression found it. In general, the conditional expectation can be any measurable function of x. Approximating it with a neural network is, literally, what machine learning does. Next, how these 3 ideas, filtration, expectation, and conditional expectation, power every formula in phase 2. 3 ideas: filtration, expectation, conditional expectation. One formula unites them. Vt equals the discount factor times the risk-neutral expectation of the payoff, given ft. This single line governs all of phase 2. The yellow piece, present value, the Q in purple, the risk-neutral measure, a change of probability, green, the payoff, teal, the information available at time t. Every color is a concept you just learned. To use that formula, we need the process driving the stock price, Brownian motion. 4 properties define it completely. 1, it starts at 0. 2, increments are independent. Past doesn't pollute future. 3, increments are Gaussian with variance equal to elapsed time. 4, paths are continuous. Next episode, we derive each from first principles. And here is the bridge. Conditional expectation is the unique function that minimizes expected squared error. In finance, that minimization is backward induction on a tree. In machine learning, the same minimization is training a neural network. One object, two machines. The math behind finance and the math behind AI both run through this. Thank you for watching. See you in episode 7, Brownian Motion.